Yes, hello good people, welcome to this video. I'll be recording a video that comes from the subtopic that is pulleys and connected particles, and specifically we'll be looking at inclined planes. Now when you look at this, we've been told that this is a rough plane that is inclined at an angle of theta to the horizontal, where the value of tan theta is 4/3. So it's just wise for you to get what exactly is the value of cos theta and sin theta. So you can just form a small right angle triangle over there. Opposite is 4, adjacent is 3, and this is the angle, so this one should be 5. You can use Pythagoras to get that. So the value of cos theta, you'll get it's 3/5, and the value of sin theta, you'll get it's 4/5, and that's what you'll be applying to ensure that everything goes on well in our calculations. Now once we have all that, it's now time to embark on our job. In this case, we are also told that the string passes over smooth pulley. Pulley smooth meaning that tension is the same on both sides, and then the string from P to the pulley lies along the greatest slope. As you can see, the other end of the string is attached to the bucket. The package P has a mass of 1 kilogram and is held at rest on the plane. So if it's at rest, the upward forces but parallel to the plane should be the same as downward forces but parallel to the plane. And then the bucket of mass 0.45 kilogram hangs vertically, as can be shown over there when the string is taut. Then the coefficient of friction between P and the plane is mu. When the small block of mass 0.2 kilogram is placed in the bucket, the system is released and remains at rest but at limiting equilibrium with P at the point of slipping. Now when you talk about limiting equilibrium, that's the point where it's in between resting and slipping down. There it means that friction is the one that's holding it in place. So we need to get sure that the value of mu is a quarter. Now one thing you should be able to know, that the weight acts vertically downwards, and then whenever you place something, there's normally, they are called normal forces. We have the normal action force and the reaction force. They are normally perpendicular to the plane. This angle is the same as this angle over there, and therefore we can be able to get the component of this that acts parallel to the slope, which is just W sine theta, and the one that acts perpendicular to the slope, it's W cos theta, because it's adjacent to the angle. So this is what I mean. That force W acts downwards like that, and then if it's acting downwards, we have it's acting downwards, but you're having an angle of theta over there. So the one that acts parallel to the slope can be taken as this one here. Remember, this is opposite, this is adjacent, and this is hypotenuse. So to get sine theta, sine of this theta, we just have to take the opposite divided by hypotenuse. So to get the opposite is basically h sine theta, and then to get the adjacent, to be able to get, it's that a cos theta. So that's the knowledge that we are linking to apply it over here. So we have everything set with us. Just want you to have a look at this. This W cos theta is the one that's pulling it down as a result of the weight. So that is W cos W sine theta, I'm sorry, W sine theta, and the one that acts upward is just W cos theta. That one acts perpendicular to the slope, and then friction acts upward because this thing we've been told it's a limiting equilibrium, so the friction is the one that's holding it in place. So it should be acting in the opposite direction of slipping. So if it slips downward, what results with the slippage is this force. So friction should act against it to counter its effect. Now we are now good to go. We can now start. When a mass of 0.2 kilogram is held over here, so we have inside here 0.2 kg, so meaning that the total contents is going to be 0.65. So now that this string is light and inextensible, so the tension should be the same. So the bucket is pulling the pulley and the pulley is pulling the bucket back. The same to this, the mass is pulling it, this package is pulling the pulley, and then the pulley is pulling it back. So this is tension. Tension is the same on both sides. Now we can start. Let's consider the idea of balancing these forces here. So we can say that tension plus friction, because all of them they operate in the same direction, should be the same as W sine theta. So we are saying if it's at the point of slipping, those force that's acting upwards must balance with the same that the force that act downwards, and the forces that are acting up the slope but parallel, we have tension and friction. So we need to get friction first. Friction is given using the formula mu r, and therefore our r is given by, we got is W cos theta, and our W is basically the weight. The weight is the mass, that is 1 times gravity. The mass of the package is 1 kg and the gravity is g. Then cos theta, we got it to be 3/5. So this one is going to give us 3/5 g. So that's the normal reaction force. So our friction becomes mu, so that's 3/5 mu g. So that is what we have. Now our tension is going to be 0.45 plus 0.2 multiplied by gravity, which is going to be 0.65 g. That's basically the force that's pulling this. We can just say it's just the weight of the bucket that's pulling this mass over here. That force is evenly distributed along the string. Now one more thing, to substitute, we also have W sine theta. We can solve for that. W, remember, it's the weight, and we got it's 1 kg times gravity. Then sine theta is 4/5. This one is giving us 4/5 g. So let's replace everything that we have. So this is going to give us our tension, that is 0.65 g, plus our friction, which is 3/5 mu g, should be the same as our horizontal component. Okay, I mean like the force that's acting down the slope but parallel, which is given by 4/5 g. So if you cancel the g's, you are going to have 0.65 plus, when you convert this one to decimal, it's 0.6 mu, which is the same as 0.8 when you convert this to decimal. By the way, all the fractions that have got 5 or 2 in the denominator, they are terminating, they are not recurring, so there we can be able to convert them and deal with them as decimals. So here we are going to have 0.6 mu equals to 0.8 minus 0.65, which is giving us 0.6 mu equals to 0.15. So if you divide both sides by 0.6, this one is giving us the value of mu as 1/4. So this is what you're supposed to show in that part of the question. Now we can proceed to the second part of this question. I think I've copied the diagram and the question in the next page, so it'll be good to go. So we are having additional blocks, additional identical blocks of mass 0.2 kg are added one at a time until the bucket starts to move up the plane. So basically we are going to add inside here another mass of 0.2 n. Now what am I talking about? You know, when you are adding some additional blocks each of mass 0.2 kg, we don't know how many there are, so there are n of them. So n times the mass of each, that is it. So this one gives us the total weight of the bucket to be 0.45 plus 0.2 n. So this is now the tension. In this case, the tension has actually changed. Now again, we know that there is a disruption of equilibrium. When you add this one here, this bucket moves down, and as a result this one moves up. So if this one moves up, then what happens? The tension is the one that's pulling it up. At the same time, there is also friction, which acts in the opposite direction together with the WG sine theta. No, just W sine theta. You know, W sine theta is basically that force that's pulling this object down as a result of its weight. Our value for normal reaction force remain the same, so that is G cos theta. We had already resolved all of them, so this is the W. So we can now work this question out. Still can say that the forces up the slope should be the same as forces down the slope. So what happens in this case, whenever we take tension, should be the same as W sine theta plus friction, and we had W as G. If you can remember, W is the same as the mass of the package, which is 1 kg, times G, which is giving us G. Then sine theta, we had already calculated it. If this is a 4 and then this is 3 and then this is a 5, then what happens? Sine theta should be 4 over 5. Then plus mu, we got it as a quarter, times our normal reaction force is actually G cos theta. So it will be G multiplied by cos theta, which is a 3 over 5. And this is the same as our tension. Our tension, we got it over here, which is a 0.45 plus 0.2 N G. So if you work this one out, we will be able to get 0.45 plus 0.2 N. So let's cancel the G's all over. No, G's are all over, so we can have this one equal to 4 over 5 plus 3 over 20. So this means that our value of 0.2 N should be the same as 4 over 5 plus 3 over 20 minus 0.45, and this is giving us, we can convert these ones here, so this is 0.8 plus this 0.15, and then this is a 0.45, which is the same as 0.2 N. So balancing all of them, we are going to have 0.2 N equal to 0.5. If you use your calculator, this value gives you 0.5. Dividing both sides by 0.2 gives you the value of N as 2.5. So since this one we are modeling, then this means that they were just 3 blocks. Yeah, so the value of N should be 3. So they were addition of 3 blocks of mass 0.2 kilogram that resulted in that mass being pulled up the slope. Now we can continue to the next question and solve for, we can actually solve for, we are being told to solve for the magnitude of the initial acceleration. So in this question we are going to apply Newton's second law of motion, which gives us the formula F equals to ma. Now what happens, remember there is friction that is acting in the opposite direction of motion. There is tension on the string that's pulling this mass up. Then there is that component of the force, component of the weight, which is G, that's pulling it down. We got it as G sine theta. Then we also got that component that's equal to the reaction force, that was G cos theta. So I think we have everything that we need. And then here there were 3 blocks, each of mass 0.2 kg, that were added. So meaning that we are going to have 3 times 0.2 plus 0.45, and this is going to give us 1.05 G as now the weight, which will be the same as the tension. Now since in this modeling we are assuming that this string is light and inextensible, then it means that the tension is the same on both sides of the string, and therefore the acceleration is the same. So the acceleration that this one I mean, like, whatever resulted to acceleration of this mass of the block is the same value that's accelerating this block. Okay, what do I mean? I know I'm not making sense in such a case. So the magnitude of the acceleration of this package is the same as the magnitude of the acceleration of the bucket. That is what I was trying to communicate. Now let's see. We know if we resolve up the slope in parallel, we know that you're going to have the tension minus friction minus g sine theta, and remember sine theta we got it as 4/5, should be the same as the mass of the package, which is g, times the acceleration. The mass of the package is 1, sorry, it's not g, and this is going to give us t we have it, that's 1.05 g, minus friction, that is a quarter. Okay, let's leave it like that. We can be able to get two equations in terms of t. So we have t minus friction, which is a quarter, times the normal reaction force, we got it as 3/5 g minus 4/5 g equals to acceleration in that case, and this is going to give us t minus, this is 3/20 g minus 4/5 g equals to a. So this one gives us that our tension is the same as acceleration plus, this is 0.15 g plus 0.8 g. So our tension should be the same as a plus 0.95 g. In case you're wondering where these values are coming from, when you convert this one to decimal, you get this. When you convert 4/5 to decimal, you get 0.8. So this one is our first equation. Now let's consider the motion downwards after those three masses are added. So when you consider the motion downwards, now if it's moving downwards, then it's a clear indication that the weight is bigger than the tension. So if you do weight minus tension, should be the same as ma, and our weight is 1.05 g minus tension should be the same as mass, which is 1.05. That's basically the mass of the bucket together with the mass of the contents multiplied by a. So if you take t on the other side, we are going to get t equals to 1.05 g minus 1.05 a. So let's equate on both sides. This is our equation 2. This is our equation 2. Right, now let's have a plus 0.95 g should be the same as 1.05 g minus 1.05 a. So we are doing this, tension is the same as tension, so we are just equating 1 and 2 directly, so meaning that we can have 2.05 a equals to, the other side is 1.05 g minus 0.95 g. This is giving us 2.05 a equals to 0.1 g. So if we divide both sides by 2.05, this value that you are getting as a, you can either get it as 0.478 meters per square second, or you can work this value as a decimal in terms of g, so here by 100. So just get the value from your calculator, and it's really giving me this value here. So 0.1 divided by 2.05, that is 2/1 g meters per square second. And that's the end of our video. Feel free to keep coming and check the contents uploaded. The video has been slow, it's lengthy, but it's very educative. Thank you so much for watching, and refer to your friends.